Okay, let's continue with the structure of the atom. Yeah, we'll get to that. But first I need to finish this description of the discovery of the nucleus. Uh-oh. Must have picked the wrong one. There we go. Okay, so we're continuing. Discovery of the atomic nucleus and I was telling you about Ernest Rutherford, and we covered some of his experiments. Yeah, Drew.
Which one, Thomson's model of checkers? Because you already talked about that.
Oh, well, that's what I'm going to get to now, is how Rutherford proved Thomson's model wrong. Thomson had this idea. I mean, we know now that the atom consists of a heavy positive part and these light little negative particles, the electrons. But Thomson just figured, well, what the structure of the atom is, you have this this heavy material that is positive spread out over the whole atom, and then you've got these little negative electrons embedded in it. Okay, my parallel being the muffin with the little raisins in it. Okay, now Rutherford thought about that model, and it occurred to him that there was a way to test it. That, think of it this way. Let's say you have a well, let me just so the subject here is testing Thomson's model. Now, imagine you have a baseball, and you're throwing it at a whole bunch of these big muffins, okay? Or, well, let's make them even bigger. Let's make them like cakes, okay? So we got a whole bunch of cakes here. These are our, this is equivalent of our atoms, okay? But the positive stuff in these atoms is spread out over the whole size of the atom. Okay? Now you throw something at it. So it's like, a baseball you're throwing at, a whole bunch of these big cakes. Now, the baseball, when it hits one of these cakes, right, is going to get slightly deflected. But baseball isn't going to get deflected very much because they're just not dense enough, right, to actually deflect the baseball very much. Yeah, Troy.
Would the baseball become embedded in the cake?
Well, I mean, if you throw it fast enough, it won't become embedded. It'll go through, right? Okay, so that's my example. Okay, you're throwing this baseball really hard, and it's going to go through these cakes, and it's going to get slightly deflected. Okay, but what if instead of cakes, taking up all the area here, you had little lead balls with a lot of space between them?
Well, then you may not.
Well, then when you throw the baseball, right, most of the time the baseball is just going to go right through. It's not going to hit the lead balls at all. But, Nick. Oh, any way you want. You can just have them on strings or something. Okay. But these are heavy little lead balls. Okay, heavier than your baseball. Now, if the baseball hits one of these things directly, what's going to happen? Nick. Yeah, baseball could come right back at you, which would never happen in the case of these cakes, right? Okay, so this was basically Rutherford's idea for testing Thomson's model. Was what if I can take these? Filling in for the baseball, we'll take these helium nuclei, these alpha particles, okay, and we'll shoot them at some material. Now, the material he chose was a very thin gold foil. Okay? Now, if the mass of these gold atoms is spread out over the entire size of the atom, then you've got something like the cake thing. And Rutherford was actually able to prove that if the mass was spread out that way, that these alpha particles should, they'll be deflected a little bit, but they'll never be deflected by really large angles, and they'll certainly never come back at you. Okay, so this is the experiment that he did. He took. Let me see. I think I'm going to switch to green here. Okay, so this is experiment 4 of Rutherford's. And let's say you have a uranium source, okay, and you have some block of lead here, say, with a hole cut through it. Okay, here's your uranium. And so you've got these alpha particles flying through at high speed, okay, through that hole. Now, he puts his thin gold foil. No, it doesn't have to be gold. But gold is convenient because it's a soft metal that you can make into a thin foil. Okay, a lot of other metals that are harder, it's hard to get them really thin. But gold's a soft metal, and you can pound it into a really thin foil. And the reason he needs a thin foil is if you used a thicker one, what would happen? You wouldn't get any alpha particles going through. Okay, he wants to have just basically a thin layer, of a few atoms here, so that most of the alpha particles go through, and he can detect them, say, over here. Now, he by the time he does this experiment, he's discovered something else, that there's a substance, zinc sulfur, okay, a zinc sulfur compound. That's the Zn is the symbol for zinc, and S is the symbol for sulfur. Yes?
Is that another sheet behind it?
Yeah, this is another sheet. You can call this the zinc sulfur detector. And the great thing about this zinc sulfur stuff is when a high-speed alpha particle hits it, it emits a little flash of light, so you can actually see where the alpha particle hit. Okay, so it makes a really nice detector for these alpha particles. Drew.
And that's just not one. That's like a billion of them.
Yeah, they're coming through here in a steady stream, and he's measuring how they're deflected by this gold. Yeah.
Or would it be one constant?
Yeah, I mean, the uranium doesn't actually decay real fast. So if you just have a small bit of sample here, there'll just be like a flash and a flash and a flash. It won't be, millions of flashes going off all the time. That would be chaos. You wouldn't be able to get the data for the experiment. Now, so what he sees is, when he does this experiment, is most of the alpha particles go through this very thin gold foil and are deflected by just small angles. They just, most of them hit, within a few degrees of this line that the alpha particles are originally going on. That's right.
Does he have another detector to the left?
Yeah, he also can set up detectors, these zinc sulfur detectors, anywhere he wants to. And, when he puts one over here, say, and over here, if Thomson's model were right, he should never see anything, right? I mean, you should never get, these cakes, would never be able to deflect this high-speed baseball backwards, right, Drew?
Now, would you ever see little tiny holes in the thin gold foil or no?
No, it doesn't actually blast a hole through the. Yeah, these are little tiny particles. They're actually, they're smaller than the gold atoms, quite a bit smaller. So they're not going. In order to see a hole in this gold foil, you'd have to, blast, billions of atoms out of the way, and right.
Do we have lasers that can go through metal?
Yeah, lasers. A high-power laser could burn through a metal if it were focused enough.
Like water, when it shoots through so fast, it cuts through metal.
Yeah, if you shoot something fast enough, you can always you can get it to go through practically anything. Now, okay, but you all get the basic idea here. And what Rutherford sees is that he does see little flashes of light in these other detectors that imply that some of the alpha particles, a small percentage of them, but still some, are being deflected backwards from this gold foil. And that disproves Thomson's idea, because there's no way, if the mass of the atom were spread out over the whole area of the atom, that there could be enough force to actually knock these alpha particles backwards. Okay, so Rutherford realizes Thomson's model is wrong, and the only thing that could explain the results of his experiment is if the atomic structure is quite different from what Thomson imagined. What it has to be is, in these gold atoms, there is the positive part of these atoms is concentrated into a little tiny area. And all the mass and the positive charge of the atom is in this little tiny area, and then the negative part of the atom, the electrons, are way out away, orbiting that nucleus. So you, instead of this raisin muffin model of the atom, what Rutherford proves is that the atom is very much more like our solar system, where almost the mass of practically all the mass in the solar system is concentrated in the sun, right? And then we've got these planets at incredible distances away that are circling the sun. Well, the parallel, there's a The atom is very much like that. Nearly all the mass of the atom is concentrated in a very, very, very small area, right in the center, and then the electrons orbit around. Yeah.
Does that make it at all possible that our solar system is in fact an atom of something out there?
Yeah. Now you made a sudden transition to science fiction. That our solar system is actually an atom in the body of some giant. No, we're not going to go there. We need evidence before we can suggest a possibility. The first person who said that, remember, was. Does anybody know who was the great scientist who laid down the fundamental rule that science does not progress by simply imagining possibilities, that even to put forward a possibility, you need observational evidence? Troy. Well, Aristotle did say that all knowledge is based on observation. But to put that, there was a great scientist who went a little further than that and said, not only is knowledge based on observation, but unless you have observation to observational evidence, you're not even entitled to imagine possibilities. Daniel. Before Lavoisier, the father of physics, Newton. And it's a good rule. One of the reasons that Newton said that was that right before Newton, there had been a very famous thinker who named René Descartes, who had invented incredibly elaborate scientific theories, completely out of his imagination. You know, he didn't have any observational evidence at all, and they were all wrong. And Newton said, "This is not the way to do science. We don't." So, not that I would accuse you of that, Daniel, but still, Okay. Let's. Okay, so we have now, instead of this muffin view of atoms, we have a solar system view of atoms. And Rutherford actually goes through the mathematics and shows that if the nucleus is this, tiny little bit of heavy positive matter in the middle of the atom, then that's exactly consistent with the experimental results he gets from bouncing these alpha particles off of his gold foil. Okay, so now we've finally gotten to the nucleus. I mean, this is one of the greatest discoveries in the history of science. And it opened up all kinds of possibilities. I mean, for the first time, people understood not just that matter was made of atoms, but that they were beginning to really understand the structure of the atom. Now I want to tell you one more thing about this nucleus before I start going on to things like bombs. I told you that, it was known that helium is 4 times heavier than hydrogen. Okay, now, let's say, given this solar system model that we have now, hydrogen is the lightest possible atom. Okay, so you figure, well, it has one positive particle that makes up its nucleus. And then it was known, of course, that hydrogen had 1 electron. So you've got 1 electron orbiting 1 little positive particle, which, by the way, Rutherford named the positive nuclear particle the proton. Troy.
Why did you change it from alpha
Oh, well, alpha particles are what uranium emits, and it turned out to be helium nuclei. But obviously the helium nuclei have to consist of more than one particle because they're heavier than hydrogen. So the hydrogen nuclei is just the proton. That's what he called the proton. That's the smallest positively charged particle. Now, helium we said is 4 times heavier than hydrogen. But it only has, the nucleus only has twice the charge of hydrogen. Now, if it's 4 times heavier, the first thing you might think is that the helium nucleus consists of 4 of these protons. But it can't be 4 because it only has a charge of 2, not 4. So what do you do in this case? Oh, okay. No. We're thinking physically here. There's no equations in reality. There's just stuff in reality. We describe it with equations. But how are we going to arrange the stuff so that we get a mass of 4 but a charge of 2? Well, Rutherford's first idea was there must be 2 electrons in this nucleus too. I mean, he only knows of two particles, right? Electrons and protons. That's all he knows. So how do you make a mass of 4 with a charge of 2? Well, you take your charge of 4 here, and you just add 2 electrons to it to decrease the charge down to 2. Now that was a reasonable idea that turned out to be wrong. Nick. Neutrons, yes. That's what actually it turned out to be. It turns out that there's a third particle that doesn't have any charge at all, but has roughly the same mass as the proton. Okay, and it took them a while to figure that out, actually. I'm not going to bother to go through the experiments on this one. You're just going to have to take my word for it because we're starting to run out of time in this class. And I had to choose between telling you about the discovery of neutrons or telling you about nuclear bombs. And I think Ben voted for nuclear bombs. So, okay, so what a helium nucleus actually consists of is, let's actually do this in different colors. There's a I'm going to switch to doing protons in red now and neutrons in green. So two protons and 2 neutrons make up that helium nucleus, or what Rutherford originally called alpha particles. And then, of course, there's a couple of electrons in a helium atom. There's a couple of electrons out here orbiting around to make the whole thing neutral. Troy?
Are electrons orbiting because of the electrical?
The electrical attraction. Right, right, because you've got this core of positive charge here that attracts the negative charges. And so that's what keeps the electrons in the atom. It's the same thing, you know, the sun attracting the planets. It's similar. Yes, try.
There are two electrons in helium.
Right.
So are they going to be in the same path of orbit, or is some going to be closer than the other one?
Oh, on the average, as it turns out, both of them are the same distance away from the nucleus. But yeah, I mean, the electron orbitals is actually a complicated topic that we're not going to get to in this course. Yes, Nick. Oh, they are not ellipses. They're strange and complicated, and you'll learn about them in a later course. Probably not till you get to college, actually. It took, there was a whole another theory of physics that had to be worked out before scientists could understand electron orbitals, and that was worked out, was beginning to be worked out in the 1920s. So another 15 years after Rutherford is doing his work. Okay, now let's well, there's one question you might ask about this. Troy.
Why do the protons and the neutrons stick together?
Yeah, that's a great question. It's exactly the question I was thinking that you might ask. Particularly since these protons repel each other, right? I mean, two positive charges, and you're putting them just ridiculously close together because these nucleuses are really, really small. So how do you put two positive charges in this helium nucleus practically right on top of one another? Well, I mean, the answer is there's a force that is much stronger than electricity. Physicists, I mean, not terribly imaginatively, but accurately called it the nuclear force. And these protons and neutrons, when they're really, really close to each other, they attract each other really strongly with this nuclear force. Now, the strange thing about the nuclear force is that it only works over really short distances. It's really strongly attractive over very short distances. But, for example, if you got these two protons, if you made them, say, 100 times further away from each other than they are in this helium nucleus, well, then the electrical repulsion between them would be bigger than the nuclear attraction, and they would fly apart. So I mean, in order to stay together, they have to be close. They're really close to each other. Troy.
So is it like r, not squared, but is it a really high exponential?
Yeah, in effect. It's, I mean, they don't actually describe it with a power of a distance. But yeah, it's I mean, rather than the force dropping off relatively slowly, like inverse square with distance, it drops off. As I said, it's not really described by a power, but if it were, you might have a power of 6 or 8 or whatever. I mean it's really fast with distance that it drops off. Okay, now the this leads to a problem with really big atoms. Imagine you have something like a uranium atom. Okay, now uranium uranium atom has 92 protons.
We're not drawing that.
What?
We're not drawing that.
No, I'm just going to write down the numbers. I'm not going to draw it. Well, maybe I will. Maybe I will draw it. Well, depending on, turns out uranium comes in two varieties, but I'll tell you about one of the varieties right now. Let me see. In this particular variety, there is 143 neutrons. Well, if it's neutral, there have to be 92, right? But all of these protons and neutrons are all stuck together in this nucleus. Sure.
So then won't the protons be far apart?
Yeah, exactly. Now they start getting pretty far apart at this point. I mean, you've got, I don't know. I mean, you have this ball of neutrons and protons. But now, say a proton on this side of the nucleus and one over here on the other side of the nucleus, the electrical repulsion is going to be greater than the nuclear attraction. So this thing is just going to want to break apart. Nick?
But the nuclear reaction of the protons closer to it.
Hmm?
Aren't the attraction of the nuclear attraction of the other ones that are closer to it keeping it there?
Yeah, they do. But you can see that the bigger you make these nuclei, the more positive charges you have in a bigger and bigger space, the more you're going to have more and more protons that are far enough away from each other that their electrical repulsion is greater than their nuclear attraction. And that's just going to lead to an instability of these large nuclei. Now, I told you this morning that, in fact, it's been empirically discovered that anytime you have atoms that have more than 82 protons, which is the number of protons that lead has, okay, when you get heavier than lead, these atoms will break apart. Yeah, Troy.
Is that why when you have X that has so many protons, that when you put it in a vacuum, like the positive, positive charges coming off?
Yeah, for uranium, it's exactly right. What happens, uranium will shoot out this alpha particle, which consists of two protons and two neutrons, and then it becomes 90 and 141, right? Which turns out to be another element called thorium. Well, thorium isn't stable itself. It'll shoot out another alpha particle. And yes.
So that means uranium is constantly changing uranium to thorium.
Right. It goes from uranium to thorium to radium to radon to, God, I forget what's after that. But it goes all the way down to lead eventually. And then it stops because lead is the heaviest stable nucleus that doesn't shoot out these particles. It doesn't want to get smaller. Yeah, Daniel.
So basically, uranium is just lead with extra protons and neutrons in it?
Well, I wouldn't put it that way because, it has different properties than lead because of those electrons and protons. It has different chemical properties. It has different nuclear properties. It shoots out alpha particles lead doesn't do. So, I mean, you could see, if you're going to say that, you could just as easily say lead is just hydrogen with 81 protons added, right? Okay. Yeah.
For uranium, like a chunk of uranium,
Yeah.
when it shoots off when some of the atoms shoot off alpha particles,
Yeah.
do they ever combine once they get smaller, and then some of them combine and start shooting off again? Some of the atoms.
Oh, do the alpha particles combine, or wait?
Like the uranium, it's been shooting them off. Then
Yeah.
do the chunks of uranium combine once they become like lead or something, or a smaller form?
Well, I mean, by this process that I've been describing, all you do is you have a series of these alpha particle emissions that eventually takes you down to lead, and then it just stops. But there's other things that uranium does which leads to nuclear power and nuclear bombs. Yes? Right, and that's what I want to tell you about next. So let me see. I only have 7 minutes left to tell you about bombs. Okay, let's there's another way that physicists discovered that you can break apart a uranium nucleus. You don't have to just wait for it to shoot out an alpha particle. If you hit it with a neutron, you can get it to break apart, turns out. Nick? Yeah, that's the key. Now, so let me tell you what happens when you take this uranium atom that we've been talking about, and you take a I'll stick with one color here. Okay, you take. Let's find a color that works. Good. Take a neutron. Okay, so that's a neutron. I'm going to call it N. And you find a way to fire that into a uranium nucleus. So uranium nucleus has 92 protons. Okay, I'm going to just write a plus in there because it's a proton. And this 143 neutrons. Now, what's going to happen? Well, what happens is that this goes to, you have this, when the neutron hits, okay, it deforms this nucleus, which is originally more or less spherical. Okay, it bends it, say, into some shape like this. Whacks into it. Okay, now, what's happened? Well, what's happened is some of these protons now have gotten further apart as a result of this collision. Now, suddenly the electrical forces repulsive forces are too big compared to the nuclear attractive forces. Yeah, Nick. Yeah, so you actually end up breaking this thing in two. And I'll tell you what it goes to. What you end up with is it breaks into two other nucleuses. One that has 36 protons and 55 neutrons, and that atom is called krypton, and And then it breaks into the other nucleus is barium, which has 56 protons and 86 neutrons. Troy.
What about that neutron that pushed into it?
Oh, well, I mean, initially, I think what happens is it gets absorbed, but once this thing breaks apart into these two pieces, if you add up the numbers, you'll see there's a few neutrons missing. So you end up with 3 neutrons. Extra. Now, the really exciting thing about this is that you haven't just, barium. Now, here's the good part. Not only do you break it apart, but it releases an enormous amount of energy when you do that. That these nuclei fly out at high velocity, and the same thing with these neutrons. So it's just like in a chemical explosion, you at first just have materials where the molecules are moving around with their normal speeds, but then when you have the chemical reaction, it releases an enormous amount of energy. I mean, if it's like, say, dynamite, and suddenly the molecules, after they've reacted, have much higher speeds, and there's light that is emitted. Well, it's the same thing here. Only in the case of nuclear reactions, the energy released is much, much, much greater. It turns out that this reaction that I've just described for you releases, let me see, it's 7 million times as much energy as the chemical reaction of dynamite, of TNT. 7 million times more in this nuclear reaction. Drew.
Will they always break up in those two certain numbers? or
Yep.
they always
Every
break
time they break apart this way.
Is that
Neat.
in an atom of dynamite, or?
Yeah, in one molecular interaction of dynamite compared to this one nuclear reaction, this one is 7 million times more powerful. Yeah, right.
Now, all the radiation that results from one of these reactions, is that because of one of those atoms that's created?
Yeah, I mean, it's but in addition to these neutrons, there's also high energy light that's emitted too. Now, I'll finish this story next time, but notice that there's something, I mean, Nick mentioned something called a chain reaction earlier. Notice you've got a bunch of neutrons left over here, which can bang into other uranium nuclei and start the whole process again. So it just keeps going. And if you can get it to keep going, that's what a nuclear bomb is. I'll tell you a little bit more about that next time.